I believe this is where we left off with the SIR model, which we're now going to make into the SEIR model. So whenever you're about to do something new, you want to resave the code. So let's save as, and you have the SIR model, just add an E for the exposed group to the model and save it that way. Then we want to go to the top and just begin changing our code from the very top. So let me actually expand my code window. So the name in the comment should be SEIR. And remember, you can play this video back at any speed that's comfortable for you. And you can pause it at any time if you need to catch up. So there we go. I wrote this a while ago, but we now are going to have the S, E, I, and R variables. Okay, and I don't know the last time you ran this what your parameters were set at, but why don't you match what I have right here? So pause the video if you need to change your parameters, but I'm running the code with these parameters that I'm showing right here. Okay, so if I run it, you can see the graph actually already in place, and it has everything that's there, except there's a new feature on my graph that I don't think you had in your code. All right, so the new feature is that I added a legend to the code. All right, so let's figure out where the legend is. It's only in plot choice 4. If I put any of the other plot choices like 1, we don't need a legend, because if I have, if I'm simply plotting the susceptible versus time, I don't need a legend to tell me that curve represents a susceptible population. But when I go to plot choice 4, I have a lot of things happening. Okay, there's going to be a new category, the exposed category, that I need to worry about. So let me be sure to get that into the graph now. Okay, so let's get this legend in place. We're going to make some updates to it, but let's see how to get that SIR legend, which you probably don't have yet. So it's in plot choice 4, so I'm scrolling all the way down to case 4. And the one line of code that I added was this line of code right here. Okay, now it's important that you do it in the order SIR, because if you look at the plot statement up here, the plot is time versus S, time versus I, and time versus R in that order. So we'll try to keep everything in the order in which they would occur on the timeline. So that way, the legend automatically assigns S, I, and R to the color of the plots in the order that they came. So the other part of this legend command that you'll notice is that the location of the legend is southeast outside, right? So make sure you type it in exactly that way. Location just tells Matlab where to place the legend. So southeast, if you were looking on a map, would be the bottom right. By putting the outside in there, it won't interfere with the graph. So there will be times where if we had that inside or just left the outside off, it would be covering up what we wanted to see. So that allows you to have a legend that looks like what I have. Okay, so run your code when you add that and make sure it looks like the figure that I have here produced. So let's continue on. What we really need to do in this video is add E. Okay, like I said, pause if you get stuck and make sure everything agrees. Rewind the video if you need to. But we need to add E. Now, if you look at the list of equations that you have, all right, we also added another constant, C. So A gets us from S to I originally, but now A is going to be the link from S to E. B will be the link from E to I, and C will take me from I to the removed category. Okay, so I need a third thing, C. And let me make the C value let's see, so our rate of going from E to I is 0.5. Let's make my my C value, I'm going to make that 0. I'll make that 0.5, but I'm going to change the B value. Actually, I'm going to change the C value to a 1. So this will tell me, okay, so this will be, so A will no longer be the infection coefficient, okay? This is the coefficient for S to E, we'll say, and the units are weeks. I'll use WKS raised to the -1. All right, and this next coefficient is the coefficient for E to I, and that will be weeks raised to the -1. Okay, and what a 0.5 means is that about half of the exposed population will move to the infected pool per week. All right, so it takes about 2 weeks for the whole population to move over, which corresponds pretty nicely to the data that we have on COVID-19. So this will be the coefficient for I to R in weeks to the -1. By making that a 1, about 100% of the population that was infected will move to the removed pool. That's probably a little bit high. Let me actually make that a 1.4. I'm sorry, it should be a little less than that, more like a 0.8. Takes a little longer than a week for people to go from being infected or infectious, if you like, to being removed. So we'll make that a 0.8. About 80% of people who are infected will go to the removed pool each week. That's what that number means. Okay, Tmax, we have that at 52. That's still fine. I'm going to change something else here. I'm going to change Imax to Ymax. There's a reason for that. Right now, Imax was just, we were using that for the infected graph, but I don't want to just look at the population that's infected. I want to be able to look at the population that is susceptible, exposed, infected, or removed. So I'm just going to change that to a Ymax, and you can see Shift-Enter popped up. That would allow me to change Imax everywhere to Ymax. Right, so that should take care of it. If not, we'll have an error later when we run the code and we'll fix it then. Okay, so now we're going to move down to plot choice 4, or plot choice, and there will now be 5 plot choices, right? We need to add a plot choice 4. Oh, I'm sorry, we need to add it right here. 2 will become exposed. 3 is now infected. All right. 4 will be removed, and now we need to add 5, being all of the graphs. So that would be the combination option of all of them. Okay, so that's what we'll do. Now when we get down to the plot choices, we'll have to accommodate that we're going to put an E in between the S and the I, and that what was plot choice 4 is going to become plot choice 5, and we'll need to add the line for E to that graph. Okay, so let's continue. Moving down here, let's see, initializing vectors. That looks good. You can see though we're missing something. We don't have the E vector. All right, I probably should have written S first, and then E, then I. Let me actually correct that now. Let's just keep everything in order. The more structure and order you have, the easier it will be to keep track of what's happening in the code. So I simply cut and pasted I. get rid of that blank. And let me put E in between, and we'll have the same line of code, the zeros, 1, comma, NT, to create space for the data, for the exposed data. Okay, so this will be the exposed, whoops, vector. So that's just space and memory to hold on to that data. So now we have them in order. That's better than the way it was originally written. SEIR. Okay, and we give an initial infection amount. We set that equal to what was in the parameters, because if we have all zeros in the infection vector, as we start doing calculations, there will be no infected people to start with to begin the epidemic. Okay, now we get down to the calculations. So remember, before we had S going to I going to R, so you can see S, I, and R, and in between, there's a DI in between S and I. That's really DI dt in calculus speak. That is the differential equation. And between I and R, we had a differential equation. But now we're not going from S directly to I anymore. We're going from S to E. Okay, so we need to have a DE line. And DE, actually, let me change this. Let me go back. The flow rate to the infected group is now, if you look at the differential equations that we wrote down from the last video, okay, the rate at which people flow into the infected pool, I'm sorry, the exposed pool, is A times I times S. But then we have to subtract B times how many are in the exposed pool. So people are flowing out of the exposed pool, but the rate at which they flow out is dependent upon how many people are in the exposed pool. So if, I think we decided that 50%, yes, B is 0.5. So if 50% of the people who are exposed are leaving every week, we need to multiply the 0.5 times the number of people who are in, or the proportion of people, I should say, who are in the exposed pool to figure out how they have flowed into, I'm sorry, to account for people leaving the exposed pool, right? So now, how many people will be in the exposed pool in the next time step? That's what this will calculate for the next time step, how many people will still be exposed, all right? That's simply going to equal E of IT plus the rate at which they're, whoops, D capital E, times how long the time step is. Right now I have that at 100th of a week. Okay, so that's actually every few hours we're doing another time step, so that should give us a lot of precision. So this is giving me how many people will be exposed after each time step. And now I need to put in another line for DI. So notice I have SDEE. I better have DI before I have I. Okay, and now this is the differential equation for the rate at which people are coming into the infected pool. All right, so while B times E was going out of the exposed pool, they were going into the infected pool. So this is really DI dt. So that's the flow into the infected pool. But then we have people leaving the infected pool based on the coefficient C. And that will be times how many people are in the infected pool. So a certain proportion of the people who are infected will leave the infected pool every week, okay, or every time step, I should say. All right, and the same thing is happening here. So actually we have a rate of change in the infected pool per week that is being calculated by this line of code. And then the next line of code, which we already had, will tell me how many people will be infected at the end of the time step, okay? Then we do the same thing for going from I to R. So this won't change by much. Okay, so this is really DRDT. This is how fast people are flowing into the removed population. Now remember, once you're in, you never leave. Once you've been removed from the flow here, that's the end of the line. So there's only a positive term, but notice who's flowing in. B was the link between E and I. C is now the link from I to R. So C times I are leaving the infected pool and entering the removed pool. Okay, and then we have a line to tally up how many people will now be in the removed population. Okay, and then we use, oh, we need to change this line of code because the number of susceptible people is 1, the entire population, minus I minus E NT. Oh, and I also needed, I forgot to change that in the first line. Okay, so this is just to get the last point right. NT is the last time step. And because the loop ends at NT minus 1, we need this line of code to set the final point correctly. But we need to do the equivalent thing up here for every step in the loop. So we subtracted out from the susceptible the total population, I'm sorry, we need to subtract the exposed, the infected, and the removed. And actually below, it would be better to keep the order exposed, infected, and then removed. It's commutative. If we subtract both terms, it won't matter, but it's nice to keep it in the SEIR order as we change the code. Okay, so now we have an exposed population as well as the susceptible, infected, and removed population. Okay, so this gets us down to the plots. So we've done all the calculating now. All of the numbers exist for all 4 populations now. We just need to plot them. Okay, so let's just copy case 1. So just highlight it and hit Control C. That will copy the case. And then paste it, that's Control V, down below. And you can see we have case 1 twice. This isn't really case 1 anymore. This is now case 2, which should be the exposed population. So when we get down to the plot, instead of plotting S, we need to plot E. All right. And we probably need to have a color other than blue. So let's go with green for the exposed. So that's just a G. Okay, so I changed this so that we will plot time versus, well, the exposed population versus time. We'll keep the line with the 2, but we've changed the color to green. All right, and we want the grid on. We want everything else to be the same except we're no longer dealing with susceptible population. We're dealing with the exposed population. And then when we get down one more line, it will be exposed versus time. Okay, so that should take care of case 2, right? Now, we have a second case 2. This is now case 3 because I is the 3rd case. We don't need to change anything about that case. But case 3, what was case 3 is now case 4. And that would be the removed population. We don't need to change anything with that case. And finally, that's case 5 for all of them. So we now have 5 cases to worry about. Okay, and case 5 will need to be updated, right? We have, if you look at the plot statement, we have S, I, and R. Let's keep it in order. Let's put almost the same thing, T, comma, E, to get the exposed plot in there. Remember, we made that green. Continuing on to the next line, so that's why we have to have the ellipses. and that should put the exposed population in there. And now we need to keep on going down, just make sure each and every line is still correct. It looks like we need to add an E here. Okay, so we have to have S, E, I, and R. And once again on the next line, S, whoops, sorry about that. Didn't click my mouse properly. E, I, and R versus time. And in the legend, I will want S, E, whoops, I put a quotation instead of an apostrophe. So note that in Y label, title, and the legend, we had to add the E in the midst of the sequence. So make sure that it's in order. Now it's possible this will work, but you'll notice in the upper right corner of my editing window, there's an orange square. So let me see what it says. Looks like I left off a semicolon somewhere, so I'm just going to fix that, let the Matlab fix it for me. And I believe we are now ready to go. Okay, so let's see what happens when we run our code. It actually worked. That's rare. There's almost always an error when you run the code. So don't be surprised if your code didn't work. If there was an error, it probably means you mistyped something or misspelled something. I have a lowercase where you should have a capital, something like that. Just pause the video and see if you can find your error if your code didn't run. Okay, now you can see this actually did the removed graph because that's now number 4. So I should make sure that the things I added were graph 2. The exposed population. So you can see that that peaks somewhere around week 15. Looks like maybe around week 16. That's where I have the peak of my exposed population, and it drops off over time. If I want to see all of the graphs, I now have to use plot choice 5. Since there are 4 categories, so the 5th was to plot all of them. Okay, so now we have code that will follow the SEIR model.